When we learn the tensile test, we know that the tensile test will measure the material's property under static stress, which means the stress is almost constant or change slowly with time. However, materials may behave in a more brittle fashion if subjected to rapid impacts, like an impact blow. So under those conditions, the properties we measured from tensile test will no longer be useful. So results of tensile test could not be extrapolated to predict fracture behavior. So in those cases, to measure the fracture behavior of the material or fracture properties of the material, we need to use the impact fracture testing. So which will measure materials' properties under high strain rate conditions. And two standard impact testings are the ISOD and Charpy tests. And those impact tests measure the material's impact toughness or the material's ability to withstand an impact blow. And also, in standard tests, usually the samples are notched, so they will measure the fracture toughness of the materials. So we learned from the last lecture that fracture toughness is the ability of a material containing flaws to withstand an applied load. And this fracture toughness is very important because most of the engineering components are designed with notch and stress razors. Therefore, it becomes important to know about the behavior of materials with notch under impact loading. This is the Charpy V-notch test setting and test specimen. And the specimen is in the shape of a bar and has a square cross-sectional area. A V-notch is machined in the middle of the specimen like this. The load is applied as an impact blow from a weighted pendulum hammer released from a fixed position, has a height of h. The specimen is positioned at the base. Upon release, the pendulum strikes and fractures the specimen at the notch, and then it continues to rise to a maximum height h prime. And this h prime is lower than the original height h, so which will give us a difference in the potential energy. mgh is the original potential energy, and m times g times h prime is the final potential energy, and the difference is the impact energy, which is the energy used to break the piece of metal. So the tougher the material is, the more energy it requires to break it. So that's the impact energy and the Charpy V-notch test. The ISOD test is very similar to this. It's just the specimen, the placement of the specimen is different, but the concept is the same. So both of them are normalized test, measures the impact energy required to fracture or break a notched specimen. And the energy is measured by the change in potential energy between the initial position and the final position of this hammer. However, the results of the impact tests are more qualitative and are of little use for design purpose. For example, if we have two materials, material A and material B, and if A has a higher impact energy than B, then we say A is tougher or has a high fracture toughness than B, and that's it. The absolute values of the impact energy are of little significance. They cannot be used for calculation or for design purpose. So the impact energies are of interest mainly in a relative sense and for making comparisons only. Perhaps one of the more primary functions for Charpy test is to determine whether or not a material experiences a ductile to brittle transition with decrease in temperature, and if so, the range of the temperature. Well, this phenomena, ductile to brittle transition phenomena, we have seen it earlier. If you still remember the pipe, right? Pipe made from PVC or pipe made from other materials, and it can be ductile in summer when the temperature is normal, but it becomes very brittle at lower temperatures. For example, in winter, it will shatter into pieces. So that's the ductile to brittle transition phenomena. And a lot of materials will experience this transition with decrease in temperature. And with the Charpy test, we can figure out the transition and the range of the temperature. There are two ways to figure out that. One is by the appearance of the failure surface or fracture surface versus temperature. And second is we plot the impact energy versus temperature to see the transition from ductile to brittle. So the ductile to brittle transition is related to the temperature dependence of the measured impact energy absorption. In this ductile to brittle transition, temperature is defined as the temperature where the failure mode of the material changes from ductile to brittle fracture. We should mention that not all of the materials has this behavior. For example, some FCC metals do not exhibit the ductile to brittle transition temperature or transition phenomena. So we'll see that later. But basically, this is a curve, impact energy versus temperature plot, resulted from a series of Charpy tests. So to get this plot, we perform a series of Charpy tests at different temperatures. For example, first we perform the test at 80 degrees Celsius, and we measure the impact energy. And then we change the temperature. We lower the temperature to 40 degrees Celsius. We measure the impact energy and continues to lower it to measure the impact energy at different temperatures. And then we connect the data point to get this impact energy versus temperature curve. So this is how this curve is measured. So now, how is the impact energy and temperature related to ductile and brittle? Well, at high temperatures, here's the relation. We have a large impact energy, and large impact energy corresponds to a ductile mode of fracture, whereas a small impact energy on this side corresponds to a brittle fracture mode. Now we can see at higher temperature, this energy is relatively large, and as the temperature is lowered, the impact energy drops suddenly over a relatively narrow temperature range. And below this temperature range, now the energy has an almost constant value, but it's very small, which corresponds to a brittle fracture mode. And the temperature, well, again, it's a range of temperatures rather than just a single temperature point. But this range is relatively narrow. In this plot, it shows the transition temperature. It's this specific temperature, but again, it's very hard to tell. It's not really easy to tell which specific temperature the transition happens at. So we just mentioned that not all materials have this ductile to brittle transition behavior. So here is the ductile to brittle transition behavior for different materials. We can see that the low strength FCC metals, including copper, nickel, and aluminum, And also most HCP metals do not experience a ductile to brittle transition, and it remains high impact energy with decreasing temperature. And also for high strength materials. So high strength materials is defined as materials has a yield strength above the Young's modulus divided by 150. So if that relation is satisfied, we say this material is high strength material. So for high strength materials, the impact energy is also relatively insensitive to the temperature, doesn't change too much with the temperature. However, these materials are also very brittle because you can see how low the impact energy for those materials are. And the characteristic ductile to brittle transition is represented by this middle curve, and this behavior is typically found in low strength steel that have the BCC crystal structure, and also in polymers. Alternatively, the appearance of the failure surfaces can be used to determine the ductile to brittle transition temperature. So for example, we have 6A36 steel Charpy V0 specimen, and they were tested at different temperatures. The temperatures are indicated on top of each specimen. From right to left, the temperatures are from higher temperatures to lower temperatures. Now we know at higher temperatures, the material will be ductile versus at lower temperatures, the material will become brittle. So for ductile fracture, the fracture surfaces is fibrous or dull. So this specimen is tested at 79 degrees Celsius. While for a totally brittle surface, for example, this specimen that was tested at negative 59 degrees Celsius, the fracture surface is shiny. And over this ductile to brittle transition, features of both types will exist. So how do we use this ductile to brittle transition temperature? Or where should we use it? Well, structures that are constructed from alloys that exhibit the ductile to brittle transition behavior should be used only above the ductile to brittle transition temperature, because above that temperature, the material is ductile, and below that temperature, the material is brittle. Here is a classic example of this failure occurred during World War II, when a number of welded transport ships away from combat suddenly split in half. The vessels were constructed from a steel alloy that had adequate ductility at room temperature and above room temperature, which is obtained from the tensile test. It's ductile at room temperature. But this brittle fracture occurred at a relatively lower ambient temperature, but it's not that low though. It's 40 Fahrenheit, about 4 degrees Celsius. So that means this steel alloy has a very high ductile to brittle transition temperature, just around the room temperature, or just a little bit below the room temperature. And that is why it has this brittle fracture in a sudden.